Hi, everyone, and thank you for joining us today. My name is Jay Singh, and I will be your host for this NASA Technology Transfer Program webinar on the various small-sat technologies from NASA Ames Research Center. The webinar will be structured in a lightning talk format, so the presenter will have 5 to 7 minutes to present the technologies, and then 3 to 5 minutes for Q&A. Before we get started, I wanted to mention that the Technology Transfer Program has over 1,000 patented technologies across the entire agency and 100 different technologies at Ames available for the public to license. In grouping our small set technologies together, hopefully you'll come away with understanding the numerous ways they are related. Ames Research Center has been a pioneer in developing and flying small set technologies. While this is not the focus of the event, please note that NASA has a small satellite virtual institute where you can get the latest news and stay up to date on small sat information. I'd also like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the Q&A box and we will answer them during the Q&A session at the end of every presentation. So thank you again, everybody, and welcome. These are the two links that we wanted to show today, the technology.nasa.gov, which is where you can find the 1,000+ patented technologies, and the nasa.gov/smallsat institute, which showcases all of the smallsat news that is going on in the agency. So at this point, I'm going to turn it over to our first presenter, Paul.
Okay, good afternoon, everyone. My name is Paul Wersinski. I am the ADEPT project manager. I'm going to describe an advanced design of a heat shield, a deployable heat shield for potential applications for future NASA missions. Next chart. So let's start this video. This is going to give a little bit of a visual of what we're talking about as far as a transformable hypersonic aerodynamic decelerator. Basically what we're looking at is, to date, NASA has used rigid heat shields for delivering successfully, by the way, payloads to various destinations. But we're also looking at scenarios where the launch vehicle shroud actually limits the size of the heat shield that you can deliver to a planet. And what you're seeing here is very much like an umbrella, the heat shield deploying in space before entering the planet. This allows the heat shield to achieve a dimension, a diameter greater than the launch vehicle that carries it to the destination. Let's go to the next chart and another video. So what you're seeing is some of the prototyping and ground tests that we have been doing on this ADEPT technology. And as you can see, it is a heat shield, and we're working on it in a lab here. And we've worked on it at various scales. And in particular, we're focusing on the small sat scale, which is roughly about 1 meter in diameter for the ADEPT deployable. The key technology that we're checking out in these videos, and especially this ArcJet test, is the performance of the carbon fabric, which forms the primary drag surface of the deployable ADEPT. And as an entry vehicle, it has to survive the high heating temperatures that planetary probes see upon entry. And so here you're seeing an ADEPT about 14 inches in diameter, 35 centimeters in diameter, successfully surviving an ArcJet test, simulating a 1-minute entry at Mars. About 2 years ago, we performed a suborbital rocket test of a deployable ADEPT that took us up to over 100 kilometers apogee. So we were free of the Earth's atmosphere, and we deployed in space about a 70 centimeter diameter ADEPT, about 35 inches in diameter. And this demonstrated our ability to package, fold it up in the launch vehicle here. And as one can expect sometimes on these videos over the web, there can be some glitchiness, but you're getting the idea of the launch. And so this was out of White Sands in New Mexico. And the launch from launch to recovery took roughly 15 minutes. And that's very typical for a suborbital launch. So our success criteria was successful deployment in space. And what you're going to see is a GoPro camera that we carried. And that clearly showed that we were successful in deploying in space. We also had recording devices on board to record our flight performance. All went successful. Let's go to the next chart and get through this talk quickly here. So we're now currently looking at various small sat applications, and one that is quite interesting to us is working with JPL on a methodology of using this drag skirt for the Adept to slow down a spacecraft arriving at a planet to put it into orbit. Next chart. And as you can see here, we've looked at different scales of the Adept, all the way from what we call a 1 meter diameter nano Adept, all the way up to 23 meter configurations that would launch and deliver a 20 metric ton payload to the surface of Mars to support human exploration. So this technology is applicable over a broad range of applications. Next chart. So I think this is my last chart. Essentially, we're looking at this technology for different mission applications. And obviously, this would fill a niche where you are constrained by your volume as far as a heat shield for delivering your science payload to your destination. We've made great progress to date, and we are eagerly looking for potential mission applications to further this technology along. I think with that, I'll pause and see if we have a little time here, or I still have any more time left on my talk. Thank you very much, everyone.
Thank you. That was great. And if you have any questions about the technology, please put them in the Q&A. We can answer one question. So one question we got is, how is this comparable to regular heat shields in the terms of cost to performance?
That's a good question. On a cost basis, it's basically filling a niche. And so you would expect probably some higher cost as compared to a traditional heat shield. But keep in mind that we're looking at applications of this where a traditional heat shield would just simply not be applicable. So it's a little difficult to do an apples to apples comparison for, we wouldn't envision, for instance, using this technology where a rigid heat shield could perfectly satisfy all your mission requirements. Okay?
Hey, Don, take it away.
All right, hi, I'm Don Soloway. And why don't we just go to the next slide and I'll talk about what the title means. Okay, so what I developed here is a way of doing relative motion control of a cluster of nanosats. I use two technologies. I use electromagnets for the control authority, and I use magnetometers for relative position determination. The main things that I developed, and there's a lot more that's in the patent than what I'm putting here, but the first thing was I developed the nonlinear coupled force torque equations for a cluster of satellites, specifically for n number of satellites, derived them and solved them for controls application. And then for demonstration purposes of control, I developed a nonlinear control law that had been developed for the n nanosats, and n being any number you want to pick, integer, of course. To test it out as a demonstration, I developed a 3-DORF simulation to validate the equations, both the force torque and the control law. And now I had started, I built a 3-DORF hardware. It's been designed and built, not fully tested yet. So they wanted a picture of what technology looked like. It's an electromagnet and a magnetometer. So I showed more of an example of it's being used as inside of a fractionated satellite where you want to keep the nanosats close together. The way it would be configured is each satellite would have 12 electromagnets, one on each of its legs, which will allow us to have multi-dipoles for use of very fine control and positioning. The benefits inside of this is if the application is fractionation, whether it's heterogeneous or homogeneous, you have the benefits as a well-studied area of fractionation of satellites, but I'm bringing it to nanosats. And it's increased reliability, reduced non-recurrent development costs, reduced time from mission concept to flight, reduced mission operations. The benefits of using this technology is it's non-propellant based. So it's using electricity, which of course is a renewable source, and you'll be able to get that from solar panels. Sorry, I just got distracted. If you look at the other electromagnetic approaches for controlling satellites, MIT had done a lot of work in this area over the last decade or so, but they were looking at satellites, launch satellites, miles apart. So one of the downsides to that is, doesn't matter how many electromagnets you use at a satellite, that far apart, it shows up as a single dipole. Thus, it requires using a reaction wheel for when they're on axis pointing at each other, there is no control authority. So they must have a reaction wheel to resolve that 1 degree of freedom. Here, having a multi-dipole configuration, there is no need for a reaction wheel, there's just no moving parts, and not having moving parts in space is always very good. And also, by using a magnetometer, and I'm building off research someone else had done, that they were able to get down to the single-digit millimeter accuracy for positioning using a magnetometer and electromagnet that we'd be able to use for positioning the nanosats relative to each other. Next slide, please. Okay, here's just an example of an application. If we did functional fractionation, you could break the satellites up into, say, 4 different things: solar power units, navigation unit, communication unit, and science payload. Benefit there is the design team only pays attention to the science payload. And if they need more power, they just add another solar power unit versus needing to design in, do I have fold out solar panels? Do I need to, you know, typical problems that come in designing of one unit, everything in one, all in one. The other beauty of this is that if they're all separated, say the solar panel unit could actually be positioned to be a sun shield for the science payload if it's needed. In terms of mission operations, usually, you know, a lot of times you'll need the payload to point one way, and then later on communicate back to Earth, you need to point the other way. Here, if you have a communication unit separate, it could always be set up just to point to Earth, whereas then the operations is just on science payload. But these are the benefits of fractionation. My technology enables this for inside the nanosat, small sat domain. All right, next slide, please. This is where if you did homogeneous fractionation, again, mine enables the ability to do fractionation. A lot of work out there on fractionation. You can look up all the different ideas for fractionation. But you could use it to then bring together a much larger solar array. All right, next slide, please. As I said, I developed a 3 degree of freedom simulator. Here I have a graphic of 4 satellites. The different colors are indicating whether it's North Pole or South Pole. And here I took a snapshot while I was in the middle of controlling them to move from 30 centimeters to 20 centimeters apart, so they're moving in. Over here, I plot for myself the control error. Up here are all the detailed parameters I need to know just so I know things are happening the way I'm expecting them to happen. And then last thing to point out in the simulation, the max power or the max dipole moment I'm using is 1 amp meter square, which is not a very large magnet, to say the most. I'm assuming the cube mass, a typical nanosat single cube, 2.5 kilograms. And want to know more about the simulator, I can tell you later. Next slide, please. So here you see I'm started to build up a way of then testing or validating the simulator. The white bar with the red ends, that's an electromagnet, and you can see I have 4 of them placed as a cube. In the center, I have the electronics. To do this, I have a computer sitting off the side that's doing all the calculations. I didn't want to onload all the controls equations onto this. Here, we just have a wireless transmitter to get the command to tell the platform which coil to turn on and off. Let's see. The carriage and the coils are 23 kilograms, so it's about 9 times bigger than what my simulator was demonstrating. So the max dipole moment, how you rate a magnet, is I made it 8 times what I did in the simulator, just so I could have sufficient power to be able to move these. And I did get to turn them on and give it a command, and there was a sufficient electromagnetic field to be able to attract or push them apart from each other. Okay, any questions?
Thanks, Don. That was great. I appreciate it. And also just wanted to put a reminder out to everybody, if we don't get to your questions, we will follow up with you via email. So one of the first questions is, have you considered the impact of magnetic storms?
I haven't considered the impact of magnetic storms, but I'll answer it, and I'd have to look at it, but in terms of dealing with the magnetic field of the Earth, the MIT again did a lot of work, and what they proposed in their controls, which I adopted, is that each time you give a command, you reverse the polarity. So you're actually neutralizing it in the magnetic field that you're flying. So one time it'll be north and then south, and then it'll be south and north, and you alternate back, and it reduces the impact of the magnetic field around. I don't know about magnetic storms and how that would be. Okay, boy, we're getting a bunch of them. Let's see. Jay, you tell me how much time I have.
Yeah, we're running a little ahead, so we can we have a little bit of time.
Okay.
So 2 of the questions that we have here is, what is the maximum separation your technology can work with, and what language is the 3DOF simulator written in?
Okay, the language, it's written in MATLAB, and the distance, the 1 amp meter squared, is about a meter apart. That's about the furthest before you'll lose control. So a meter separation with a 1 amp meter squared coil. Make the coil bigger, you can get a little further. Remember, it's an inverse Kubes law, so making things bigger don't buy you literally more.
Hey, Don, what are the power requirements for this?
I don't have them off the top of my head. I'd have to go back and look, but if you look at that screenshot of the example, you could get a sense for that example. Again, it's only a planar one, but I do have the power that was used to do that motion there.
Oh, we have another one. Can you talk about the potential applications and the precision of the measurements?
Okay, the potential applications, again, these were thoughts I came up with. There may be many more applications, but the best one I thought of is inside the world of satellite fractionation, whether it's heterogeneous or functional. because that gives you a lot more freedom than inside the design process. You're making units that are the same, and they're thus reliability goes up, and you just plug them together as sees fit. And there's one piece that you don't see here. If you're familiar with the resonance inductance coupling, it's the way of charging something without actually having a magnetic coil that they use as proximity. Since all these have magnets, you can pass power from one to the other. So it allows for that inside of using solar as a separate unit. All right.
Oh, great. So we have one more question, then we'll go on to the next presenter. The last question would be, what obstacles do you expect you will encounter when testing on Earth?
So I'm not expecting any obstacles while testing on Earth because we have a way of mitigating Earth's magnetic field by alternating the going back and forth. Designing the unit big enough so the whatever ambient air that might be around won't impact it. What's really neat is there's this, it's called the Astrobee. It's 3 cubes that are floating around space station that if I could, the next step would then demonstrate this in space, and it can actually be done in a safe spot in space station where the hardware doesn't have to be tossed up and lost. So there's movement to actually get it into a pathway to be able to get and test it in space. But I don't see any obstacles doing it on this test bed.
Okay, great. Yeah, thank you. And for the rest of the people who had questions, we've taken them down, and we will get back to you via email with those questions. And so thank you, Don. That was great.
Do they have a way of sending you more questions that might pop up?
People can reach out to us via the Technology Transfer Office email.
All right, great. Thank you so much.
Yep. Thank you, Don. That was great. Next up, we have Richard. Richard, take it away.
Hello, can you hear me all right?
Yep.
Okay, very good. I'm going to talk about heterogeneous spacecraft networks, which was a concept we came up with a few years ago. Continue on to the first slide. At NASA Ames a few years ago, we had some visiting scholars from ESA and JAXA, and together we came up with this concept of utilizing open communication standards and commercial communications to communicate to a variety of CubeSats that were together accomplishing an Earth observation mission, utilizing 3 or more organizations. So as you might recall, the A-Train was run by a bunch of different international space agencies and was a series of satellites following each other in orbit. And based on that, we can move to small CubeSats in orbit for in the same way. So this was patented. The patent was granted in February 2018. And the open spacecraft networks, or heterogeneous spacecraft networks, applies to the use of commercial standards-based communication technology for creating open spacecraft networks for the flexible operation of coordinated small sats. So in many ways, this is the communication technology equivalent of Don's positioning technology. Once you have a cluster, you can utilize open communication standards to communicate between them up to 1 kilometer or beyond. To complement the open spacecraft networks, we have the open operation architecture, where we're utilizing the terrestrial internet to enable autonomous operation using distributed virtual operation centers for controlling the multiple satellites from different organizations. Again, we are anticipating different organizations around the world, including universities and even small private organizations, flying their own contribution to a constellation. So the application is that multiple organizations can fly these coordinated satellites. Our primary target was Earth observations, but it can be utilized for a variety of things where clusters make a difference, things like space weather and so on. And we also advocate the use of coordinated virtual operations centers for tying the different groups together to operate the spacecraft collaboratively. So we can integrate multiple communication modalities for improving mission capability and reliability. And then in the next couple of slides, I'll show you how we do that. We have a demonstration called the NASA TechEdSat, which TechEdSat 10 is right up there right now. You can look it up on the web. But we demonstrated communications technology such as the Iridium constellation for command and telemetry, along with the use of Zigbee proximity links for different elements of the spacecraft, and the use of a Wi-Fi downlink to Wallops Space Flight Center. So the benefits are we enable simultaneous and complementary data collection and distribution with higher throughput and reliability for multiple spacecraft and partners. And how we do that is we utilize more than one communication modality per mission. And the multiplication of those in a hybrid heterogeneous communications architecture is the secret here. Commercial communication can cost a fraction of the use of a dedicated space-to-ground link. And we believe that this helps promote a scalable, multi-purpose, and continuously evolving platform for technology innovation. So I have a couple of slides that show the application of it to the TechEdSat, which was one of the reasons we were able to get a patent, is we were able to demonstrate this in a spacecraft mission. Next.
Hey, Rick, these are the only slides we were able to use. Sorry about that. But if you want to continue more about the applications, that'd be great.
Okay, I can talk to that. That's too bad. The slides were interesting. So the block diagram of the TechEdSat shows the use of two Iridium modems. And one of those goes to our main control, which controlled the power for the TechEdSat. And that was our primary link. So we were able to utilize in an ISS orbit the use of the Iridium constellation in MEO just above the ISS orbit to send messages about 240 bytes each back and forth, which constituted the spacecraft telemetry and status, and we would uplink commands like turning on the high-speed processor, which utilized another Iridium network. Now, we utilized in between elements of TechEdSat 10, we utilized the IEEE 802.15.4, which is the wireless sensor network's standard. This works with multiple nodes, and it works very well as a self-configuring repairable network. So that's the use of the proximity link. Once you have proximity links, you can start to use concepts like Don mentioned, fractionation, where we have a larger satellite that hosts the space-to-ground link, and the smaller satellites communicate their data to the mothership, and the mothership links it down to Earth. So the use of MEO constellations, the use of a Wi-Fi-based downlink, and the use of wireless sensor networks were the innovations that were demonstrated over the last few missions. So that's it for my presentation. If there's any questions.
Thank you. That was great. Yeah, we do have a couple of questions. How does the SpaceX Starlink link into this, or possibly link with this?
Are you talking about the Starlink mission?
I'm assuming they're talking about the internet that SpaceX has, the Starlink array.
Okay, Starlink. Yes. You know, you're talking now about the evolving communications technology that will support small sats in orbit. Even though they're not designed to utilize, they're designed for terrestrial internet communication. What we're finding is you have adequate link margin in orbit, and you have adequate view angles from satellites to essentially close the link. So we have to we have to identify these other constellations, Global Star being one of them, Starlink being another. And as they come up, we basically can look at their characteristics and see if they can support CubeSat missions. And my guess is a significant number of them will. We have been able to utilize Iridium over a number of missions. We have a simulation of how Iridium works with a CubeSat rather than utilizing terrestrial terminals. And we can run the same types of simulations for new MEO constellations, which, as your audience can have noted, is an emerging form of higher speed internet access. And it would be wonderful if we can support CubeSat missions utilizing these evolving internet connections.
Thank you. Yeah. And somebody was asking, could you say the name of the demo mission that was there?
Yes, it's Tech EdSat. So technology education satellites. And my partner, Mark Murbaugh, has been pioneering those for a number of years. We're up to TechEdSat 10. And it acts as a technology demonstration for people like me. I can fly technology early in the game. And we utilize the services of interns from various colleges throughout the country. And we get their design help, we get their labor, and they learn all about doing missions from us in the process of doing these. We are looking at protocols. So, and we are looking at other types of radios like long range, LoRa. And how susceptible are these links to disruption? The answer is they're not very susceptible because they are meant to coexist. So they utilize spread spectrum encoding and other things that reduce the effect of interference. So we find that the use of wireless network standards work well in space. I do need to mention there are regulatory issues. One, you have to fly, transmitters flying in space require special authorization, even if they are Wi-Fi or wireless sensor network, which are completely license-free for terrestrial use. As soon as you put them in space, you require a special experimental license. So this remains one of the hurdles, but by the way, everyone has to do that with any transmitter they fly. So we believe that the regulatory issues can be addressed once there's more adoption of these communication networks for small satellites.
Great. I think we have time for 2 more questions. One of them is, how is cybersecurity maintained? And can we implement mobile ad hoc network protocols with your technology?
Yes. The protocols basically is a completely open area of additional research, and I encourage people to look at them. So things like the ad hoc source routing protocol, or the use of the delay tolerant networking. If you start to host those features aboard your satellites, your multi-way communication network can become self-managing to a certain extent. That is, the DTN, delay tolerant networking, will simply stage the data where it needs to be staged for the next downlink opportunity. So yes, we believe tremendous things can be done in the areas of hosting flexible networks. So the best thing to do is get in touch with me through the tech transfer program. You have Jay's number, and he can basically get people in touch with me for the use of such technology.
Great. Thank you so much. That was really informative. Thank you for sharing.
You're welcome.
So next up is Vade. Vade, do you want to go ahead and share your screen?
Yes, thank you for having me. The share screen is blanked out on my screen. I'm wondering, there, never mind. It's now enabled. All right. Okay, hopefully you can see a slideshow with NASA Fluid Chem. Does that come through?
Yep.
Yep. Great. Well, thanks again for having me, Jay and Kim and the Technology Transfer Off. My name is Vade Trieth. I direct the Lab for Advanced Sensing here at NASA Ames. My background is mostly in astronomy and astrophysics and aeronautics, and actually I moved over to earth science in about 2013 to focus on developing a lot of technologies from astronomy to earth science applications, and then coming up with some new techniques. So if it's all right, I'll switch the order in which I'm going to present two technologies and patents that were recently awarded for fluid chem and Midar. I figured I'd start with fluid chem and then go into Midar, if that's all right, Jay.
Yeah, please do.
Yeah. Okay. Great. Feel free to ask questions about both. I can, we can put a break in the middle, or we can just continue forward. So right now, they're both primarily ocean mapping instruments I'll talk about. Fluid chem is a passive system that is mapping coral reefs around the world, mostly on drones and larger aircraft. And then Midar is another technology that we're using that's an active sensor to look at both coral reefs, shallow reef environments, but also underwater objects, long-range communications. It's got quite a few different applications. So I'll start off with just the motivation for a lot of these techniques. As of 2020, we've still mapped only 6% of the ocean floor. We've mapped all of Mars and the Moon at a spatial resolution of 100 meters or finer in visible color bands. And so that kind of gives you a state of where we are in terms of mapping and understanding the ocean. I don't need to hopefully remind anybody, but the ocean drives everything on our planet, from our ecosystems to our protection of coastal areas. And right now we're seeing with climate change an increasingly focus on ocean systems and how they sustain life. So it's really crucial to get data on everything that's there, particularly the living organisms that are there. So for right now, looking down from space and from aircraft at the ocean is really difficult because of this challenge of attenuation. And I'm just going to make sure that you're seeing the slides. You're seeing the attenuation slide right now, right? Just to make sure.
Yep.
Okay, great. So if you look down from the orbit, this is probably familiar to anybody who does remote sensing. There's very few bands of electromagnetic radiation in which you can see through the atmosphere. So if you look at this top left plot, you can see that there's a large window in the radio bands. This is used often for radio astronomy, for radar applications, where there's very little opacity in the atmosphere. And in the visible bands, again, there's also quite a bit of transmission, and there's some in the thermal bands. Once you get into water, that problem is really amplified a lot by attenuation of frequencies from the far red, for even including the color red, all the way to the radio bands. Those are all absorbed in the water, typically within the first micron of hitting the water. So if you're trying to study and map anything underwater, you really only have the visible wavelengths of light from about 380 nanometers to 720 nanometers to see anything. And within those colors, really only the blue and the ultraviolet penetrate to a depth of about 100 meters. Beyond that, you have 99% of the energy of light coming down from the sun is absorbed. And so it's very hard to get any signal back from something that is that deep because of this problem of optical attenuation and scattering. The second problem, which is something that I developed during my doctoral degree, is this very simple phenomena, refraction. If you have two different types of fluids, in this case we have air and water, light travels differently, different speeds in these different media, and at the interface of the two, so when light travels through the ocean surface or through the surface of a pool, it bends. And if you have a flat surface of water, that can cause problems when you're looking with a satellite or an aircraft off of nadir. So if the satellite is pointing straight down, it has a nadir view of the object. If it's off nadir, it's looking away from that. And the problem, of course, with flat field refraction is that an object appears to be in a location that it does not. And the depth of the object also appears to be a certain value that it is not. If you introduce ocean waves to the surface or any type of disturbance, you can see what it does. This is a test tank in the aquarium. We're just looking at some corals at a very shallow depth from a camera above the surface. And you can see that ocean waves will also cause a lot of refractive distortions along the line of sight. So right now, there is no satellite system that is correcting for this refraction introduced at the ocean surface. We have very high resolution commercial satellites as well as governmental satellites that can see targets on land at very fine resolutions. Some of them have technologies that can help ameliorate the atmospheric seeing problems. So this would be coming from turbulent atmosphere, heat gradients within the atmospheric column. But in terms of correcting for refraction, even a flat fluid refractive state, or a fluid that has dynamics, which is the entire ocean, there is no correction. And so if you open up a time series in Google Earth and you look at a coral off of the coast of Guam, and you scroll through time, you'll notice that the hotels on the beach on Guam do not appear to move because they are georeferenced correctly. Everything in the water appears to jump around, and it's not because it's actually moving. Corals are actually sessile organisms for the most part. It's because refraction is not being corrected for in any of those images or georeferencing. So this is a big problem for just tracking anything underwater. It's very difficult if you're in earth science and trying to look at the growth or mortality of these ecosystems. But in terms of the resolution you can get in water, you'll notice that there is an intense fall off as a function of what the sea state is. It can be really bad, 10 meters, it can cause distortions, and it can go down all the way to the centimeter scale, depending on the types of waves you have present. Typically right now, the seeing limit for ocean waves on average is roughly 3-meter resolution. So if you have a satellite that can see on land finer than 3 meters, in water, typically it is limited by ocean wave dynamics to come up with a picture like that. So for something like corals, just to give you an idea of what this relates to in terms of quantifying the number or the cover of coral in a given area, most of our satellite systems have an error of about 40% to 30% error. So we do not know with that level whether something is coral or not because of this effect of the spatial resolution fall off in water. So to help fix this problem, I came up with a technology called fluid lensing, and then an instrument that is built into a CubeSat package called FluidCam. Now, FluidCam is the first 4 prototypes we built into a 1.5U platform. These are really flying high-performance heterogeneous computers coupled with multispectral full focal plane array optics. And they're just churning out thousands of frames per second over a target, and then computing from all of the processors on board, the fluid dynamics of what's going on, backing out refractive corrections, and doing a few other things I'll talk about to compute what we call the fluid lensing image. So this would be a picture that uses wave events as a lensing system. So to give you an idea of what this phenomenon looks like, and you can see this at a swimming pool or if you're by the ocean, when light hits the surface and you have ocean waves, you'll see the formation of these bright bands of light on the ocean floor, or in this case, the pool floor. This is from a synthetic test of fluid lensing on our NASA supercomputer. And here you can see that those caustics, those bright bands of light that get formed, are actually coming from wave events on the surface that focus and magnify sunlight. So most waves on Earth, once you're in the shallow regime, they tend to form waves that have a shape that is a little bit like a magnifying glass. It magnifies objects. You can see that effect at depth here over these test targets. And they also demagnify the objects. And while they're doing that, they're focusing sunlight down into those bright spots of light. So the magnifying and demagnifying events cause a lot of distortion for any sensors that are trying to look at something underwater. And then those caustics cause additional problems because they have very, very high levels of signal. So lots and lots of light is being pushed into a small area, and it's taking away light from other areas. And so you get a noise problem. So if you were to just look at one of those test targets at depth and try to get the terrestrial equivalent image and drain the pool, you'd get this top left picture of a coral. So this would be a no fluid scenario. If we add now a flat ocean layer with all of the absorptive properties of the ocean, you get the bottom left tile there that says flat fluid. Right now, most of our imaging assets from satellites as well as aircraft are doing this mean image picture in the bottom middle. So they take a picture with an integration time of about 1/10 of a second. And if you were to take a high-speed video, which is the top middle animation, you could see those wave dynamics, but most of our sensors right now are blurring them together in a nonlinear way that gives you this blurred image. And the more integration time there is, the worse that image gets. You could take a very fast picture and get this distorted frame, but that doesn't tell you the true nature of what's underneath the surface. So fluid lensing is able to compute for each of those frames a refractive solution that gives you the top right picture that corrects for the geometry based upon sensing and determination of the fluid state. It's a passive system, so we're not making any direct measurements of the surface. They're all inferred from properties of the caustics and the types of dynamics that you see in the imagery. After that fluid lensing result is created, I can then create an integration, and the integration is done by tracking those bright caustic bands. So rather than just averaging all the frames together, I use the fact that nature has provided this very bright light source from the lens to see much deeper in the water column. And so we get this integration in the bottom right. And if you compare it to the flat fluid scenario, these were acquired with the same amount of time. This is 1 second of data. You'll notice it has a higher signal to noise ratio, and actually the spatial resolution is higher because the reconstruction from fluid lensing is using positive magnification events to zoom in essentially and give you a sort of a super resolution scale. So we've been flying this instrument thus far mostly on drones and different aircraft. The sweet spot for coral reef sensing is, centimeter scale. So we're trying to get very fine scale data of reefs, but we're looking to take that platform up to low Earth orbit, either on the ISS or on a small satellite platform. We've matured the technology quite a bit for a CubeSat form factor, but there are limitations in how much light you can gather. This animation shows what some of the raw data look like from the sensor. So that was showing you all the ocean reflection as well as refraction and distortions, and then the fluid lensing solution for, this is a coral reef in American Samoa, and we've been doing lots of repeat field campaigns here. So this particular environment, we mapped at the sub-centimeter scale for the entire island. It's a data set that's a couple 100 terabytes in size, and we are using that to study coral growth and death. This is a clear tropical water environment, so the technology does, you do need to be able to see something at the bottom for it to have hope as a passive technique, but it does allow you to get a diver scale perspective of an environment that traditionally would be very, very difficult to map and survey. Sonar cannot get into very shallow environments like this. LiDAR systems struggle in very shallow environments for a lot of the same reasons with refraction. And our current system of satellite sensors and aircraft are not correcting for refraction, so they cannot give you reliable position and location and size of an object in 3D underwater in these kinds of environments. And you can see that here compared to, this is a fluid lensing result compared to a remote sensing picture on the left from a very high resolution satellite system that can get 30 centimeter resolution. In the tile 4 here, you can see some of the bathymetry from the sensor. This is an experimental technique in a lot of ways. The patent was granted very recently, just a few weeks ago, but the technology has been in development since my doctoral work, so I suppose 2013 or so. And we have been flying that CubeSat on higher altitude platforms to just mostly prove out the computing hardware to withstand that level of heat, as well as the power requirements and the cooling systems. So we recently flew over New Mexico. There wasn't many corals, but we were really able to at least get the system up and running and ensure that it can operate at an altitude of 70,000 feet and above. So I will talk now about Midar, if that's okay. And then should we do questions for both afterward? Does that work?
I keep going and then take all the questions. You're about 10 minutes in right now.
Okay, great. So Midar was actually really motivated by fluid lensing and trying to get deeper in the water column. So again, with fluid lensing, because it's passive, you're limited to that top photic zone of the ocean. I wanted to get deeper, and I ended up coming up with an idea for providing structured illumination with a sensor like FluidCam to be able to create multispectral pictures of things underwater. So Midar is the multispectral imaging detection and active reflectance instrument. It actually was awarded second place in NASA's Invention of the Year last year, chosen from over a few thousand different technologies. And it consists of a pretty simple system. There's a transmitter that has narrowband emitters. So this could be laser diodes or LED diodes, but they do have to have a pretty narrow color spread. So they're, lasers are usually monochromatic. That transmitter illuminates a target with structured light, and a receiver measures the reflectance. So you can see the receiver and transmitter setup, and you have a target of interest in the distance. These could be co-located in a monostatic configuration, or they could be bistatic, so separated out. And right now we've been identifying different chemistries and different types of high power LEDs, as well as laser diodes that are compatible with switching at these kinds of rates. And we've been building, and we've built a 7-channel airborne LiDAR, and I'll show some results of that, and some ultraviolet versions, and we're working on in the future mapping out most of the visible and UV spectrum to reach parity with passive systems. So structured optical illumination. Midar essentially illuminates an object with pulses of light from each of these different emitters. And the pulses have very specific mathematical patterns. So when they illuminate an object, they cycle through a number of different intensities, and then they also turn off completely. The receiver sees a signal, and it's monochromatic, so it just sees a sequence of pulses. But from those pulses and a database of codes, it can decode what each color band's reflectance is, and also what the reflectance of an object is as a function of the intensity of illumination source. So the best analogy I can think of nonlinear reflectance would be toast. If you illuminate an object with a lot of heat, it will change its surface properties. This is a little different. This is just before this chemistry of the object changes, you can understand its reflectance and use that to identify the material type of an object independent of its spectrum, for example. In addition to pulsing these different amplitudes for measuring reflectance, Midar can embed an optical communications packet. So for each pulse, there's actually a redundancy and a degeneracy embedded for each code. So we can transmit data on top of performing multispectral imaging at the same time. And then the way that the mathematics of Midar are set up, where we have all of the structures built into the transmitter, the receivers can actually be very simple. You can use your iPhone to receive a Midar picture and to decode a message, as well as to create a multispectral reflectance. You just have to provide the transmitter codes, and all of the transmitter has to be set up beforehand. So if we compare Midar to some of the other existing active and passive technologies, the main advantage and enabling technique that Midar leverages is these really high electrical efficiency transmission diodes. So LEDs and laser diodes that have an optical efficiency of 30 to 50%. These were not around 10, 15 years ago. They have been developed since then, and now it is energetically favorable to actually provide, essentially replacing the sun with an active illumination source that responds to your inputs rather than the solar inputs. So this is what the Midar looks like kind of in operation. This is slowed down about 1 million times. So you have the transmitter on the left pulsing its code. The receiver on the right there is the panchromatic response of the sensor. It doesn't actually see any color, but the codes that are embedded can be used to then deconstruct the multispectral reflectance. So on the right, you can see the near infrared, visible, and UV bands recovered from that picture. This can be done in microseconds, so you can create multispectral and hyperspectral videos without worrying about if you have enough light from the sun or not. You can do this during the day, although it works better at night. You have more signal. Here are some lab results from the 7-channel Midar. So this is from about 655 nanometers to 447. And we've also been experimenting a lot with the ultraviolet, which is exciting because minerals have a lot of UV pigments and responses, as well as living tissues and marine systems. So the sun right now doesn't produce, it produces lots of ultraviolet, which fortunately is blocked by the ozone hole that we've mostly patched up. But there are lots of UV remote sensing applications that have not really been exploited because of the limitations of what the sun provides.
Dave, you have about 3 minutes for Q&A.
Okay. All right. I'll just skip ahead then to the airborne results for Midar, and then we can go to the Q&A. So we've put Midar on an aircraft. You can see it flying here, and that's kind of what the bands look like when they're illuminating an object. And we've demonstrated that we can image objects underwater with it from the air with fluid lensing, and also while we're doing that, transmit data through the ocean surface while we're doing that. So in this case, we've just transmitted some pretty simple messages. But with that, I'll skip to questions and provide some publications in case you're interested for more information.
Thanks, Dave. Yeah, that was great. So there is one question we have. Is this processing done on board FluidCam, or do you need to transmit all the raw data and then reconstruct it?
Sure. So right now, because we have aircraft, we're primarily pulling those hard drives out and processing it offline. However, we spent a number of projects and research efforts to create a heterogeneous system that can process it on board. Right now, the processing time on board is about a ratio of 1 to 10. So for every 1 second of data capture, which is roughly a gigabyte or so of data, it takes about 10 seconds to compute that data down into a solution. And then we delete the raw data afterwards, so that for CubeSat applications, we have limited bandwidth for transmitting data down to the ground. So the idea was to perform that processing on board. So I hope that answers the question.
And then we have 2 more questions. Can you talk to the mass power constraints for a Midar unit, and couldn't Midar be used to image human tissue at depth?
Yes, in fact, I have a slide here on some of the human tissue applications. This was mostly looking at recognizing vein patterns, measuring heart rate and oxygen saturation with remote sensing. I haven't considered looking at human tissues underwater per se, but you could perform the same measurement and correct for the column properties there. For power constraints, Midar is very much like a radar in terms of its development. So right now we have a transmitter that has a power level. I can pull up our slide. Here we go. So this airborne version that has 7 channels is operating at about 300 watts of power. We have a prototype that is in the kilowatt to 5 kilowatt power. And then we are designing a 30 kilowatt system. So this would be 30 kilowatts of luminous output total. And it is power constrained in terms of the transmitter, but it really depends on the application. For nighttime imaging from an aircraft, you only need a couple hundred watts of power. And then it depends on your swath width as well. For in situ applications, you need less than a watt. You could perform it, on a cell phone level transmitter diode. And if you wanted to create multispectral pictures using an iPhone's camera and just add a new LED array to the iPhone, which already has a small LED system for flash illumination.
Great, thank you. That was very informative, very, very cool seeing how all that works.
Great, thanks.
Yep. So next up is Stefan Spremo, and let me share my slides.
Thank you for the charts. The first technology that I'll be talking about today is the low-cost Star Tracker software that was developed in an overall development of a spacecraft development to drop a cost of building a spacecraft by an order of magnitude, some cases 2 orders of magnitude. This particular development showed real promise in the laboratory, and we were able to achieve a Star Tracker, dropping the cost dramatically and getting the update rates to what a remote sensing spacecraft would need to operate in low Earth orbit. So the overall specs are detailed in the next slide in general. We have some restrictions. Can we go to the next slide? We have some restrictions since it's export controlled technology, but I'll just give you the general overview of what I can say here in this forum. Basically, the configuration proved out that we could do a 10 arc-second precision with approximately 8-degree field of view. And when I say cost reduction of order of magnitude or 2 orders of magnitude, this is typically a commercial Star Tracker that we've used in the past on other missions. They could range in the several hundreds of thousands of dollars range. And by using the software approach and optimizing timing and using the platform we did, which I'll explain next in my next presentation, which is called COSTAC, Cost Optimized Test of Spacecraft Avionics and Technologies, the overall enabling technologies to have this unit inside of 1 atmosphere container. And so we use a machine vision camera with special optics and lensing, and the cost drops dramatically. The other thing I want to mention about this is the feature that you might be interested in is, well, we use a specific Luminara camera and a specific lens in our application. That is not the lens or the camera you have to use, you can port it over. There's parameters in the software you can adjust for your lensing and camera that you may want to use. So this application is for small spacecraft, potentially a launch vehicle use for navigation. It's really meant for low Earth orbit, low cost missions that are meant to be up there roughly 6 months. The other thing, there is two cameras that can be used in concert, and the software handles that as well at 90-degree angles. And so there's a lot of features with the guidance navigation control capability to use this. So it is optimized in the code to run as fast as possible as well. And it does output a quaternion solution with a processor running the software. So that's about as much as I think I can say on this today. Are there any questions about this particular technology?
What kind of data FPS is required in order to use this in post rather than on board?
What kind of data? You mean a star field, or I'm sorry.
Yeah, so the question is what kind of data, and in parentheses says FPS, is required in order to use this in post rather than on board?
Oh, okay. Yeah, well, we have a star field, a database that it references and works off of. And so that is onboard software that you would fly, and that's part of the system. The external aspect of it, this is all modular software that can port over to something you're testing in the lab, or it specifically was written to work with Linux, and that has everything basically in a modular software package that can port over to a Linux platform, or potentially whatever platform you're using. Any other questions?
Can this tech, what is the hardware to use, like what hardware do you use to run the software?
So in our application, we actually were using PC-104 stacks that are ruggedized for UAV, or in our case, we were modifying them for spacecraft use. So basically, a commercial off-the-shelf processor board that has able to run Linux and has enough processing speed to run it. So all major modern processors would be able to handle this, in my judgment.
Great. And then one last question on this is, can this tech be applied towards resolving resident space objects, e.g. other satellites?
That is not an application we've evaluated. I imagine it could detect things like this, but that's maybe better handled offline, and that may be a whole nother conversation. So, other than star tracking. Great,
thanks. Feel free to go on to your next slides. Are you good to go?
Yeah. I don't see them yet, but okay. So the first technology was part of this same development. There are two separate patent pending items that are being protected by NASA, and this is cost optimized test of spacecraft avionics and technologies, COTSAT. And specifically what we're talking about today is the modular spacecraft software architecture, which is kind of an enabling aspect of what allows things to be plug and play in a spacecraft. And this was kind of an experiment about over a decade ago. We started working on this for 3 years, and I had a research team about 12 people, and we all had different disciplines, aerospace disciplines. I'm an electrical engineer and aerospace engineer, and we had a number of very talented SMEs or subject matter experts join the team. And the goal was to take the current state-of-the-art technology and drop its cost by an order of magnitude or two per subsystem, and make it modular in such a way that we focus on specific subsystems and dropping the cost individually as we did the development all in parallel. And it was really interesting what we came up with. We can we go to the next slide? So up in the upper right-hand corner is a finished prototype, and that was called COTSAT-1. And basically, we decided to put everything in a 1 atmosphere container. And this is a larger satellite that we're showing here. I want to emphasize that this technology is that big in these photos. This is a couple 100-kilogram unit, because we were doing we were looking at the boundary condition of putting a large optic on it, a half-meter optic, which would take images from space. And basically, that was the limitation of what would be allowed per the law for these types of images for this type of spacecraft. And so we went to that side of the larger scale. This can also apply to CubeSats, which I've been heavily involved in over the years with NASA since 2002, 2003 timeframe. Basically, the smaller side of 5 to 10 kilogram satellites, all the way up to a couple 100-kilogram small satellite class is what we're talking about here. This one is larger, but it scales with every subsystem. We use bigger parts, bigger reaction wheels, bigger components to actually have the system so it can be controlled at a certain slew rate and whatever other control aspects we needed it to do. So the software is what is highlighted today. And there's a number of papers that are out there on this topic and give you more detail, and I have it in the next slide, but we'll stay on this slide for a moment. Basically, this technology has an avionics system that's encapsulated in 1 atmosphere volume. And along with the software architecture, we were able to have a modular approach, which you could bring in a featured subsystem and adapt it into your software very easily, and maybe trade it out in the prototyping process real quick as well. The star tracker was one component. We had other items, reaction wheels, per coils, PC-104 stacks. We also had architecture here that there was a very robust radiation design, radiation tolerant design for controlling the power systems. And so we had software that had a number of safe mode features, or we do have. It exists in the TRL 5.6 classification, and it drives other subsystems and monitors the system health and status of all these other systems. Coupling in other features such as control systems and the star tracker and comm systems, we designed something that the reason the cost drops so much is it's like taking hardware up in a mini space station. And because it's in a pressurized volume, the extremes of space are not getting the hardware the way they would on a traditional spacecraft. And that is dropping the development cost and what you need to do to modify something to go to space by quite a bit. And so that's really the enabling factor in the hardware. But in the software as well, we also have those features where we can pull different components very easily. There's USB type interfaces, RS-232, RS-485, just standard gear that can be easily traded out. And even the comm system on this, we've had scarred the system to have up to six antennas on this this bigger satellite. So there's a lot here, and there's quite a bit of advantage in looking through the software. It's export controlled. It can't tell you, all the exact features due to those reasons, or get into the design detail beyond what I have today. So I think that's what I wanted to say overall about CODSAT. There is no prop system in this, but there could have been a prop system. The whole idea of the avionics system as well is meant to be serviceable more in the time scale of hours rather than days or weeks like another spacecraft might have. So we had special quick access clamps on the system to take it apart, get to a specific subsystem, pull out a computer. That's the general features that we're discussing here. So a spacecraft that originally probably would have cost $75 million, we're talking a scale of $1 to $5 million per copy. And there's a number of interested parties that have come and talked to us over the years and have worked with us, collaborated, and we encourage you to as well. If you have interest in this, this may have features that may enable your satellite development with what you're doing specifically. There may be something you want out of this system that could drop the cost or change your development philosophy is, to match a lower cost model. So cost optimization through software and hardware is really the takeaway of what we're doing with the system, and it's scalable from small to big. I'm not promising all features will port over to a small satellite, a CubeSat level, but there are aspects of it that may help you. So with that, do you have any questions for me?
Yeah, there are two questions so far. So with CODSAT, what about proprietary components that have their own software? How would you interface with such components? And do you follow a rigorous test regime for qualification of COTS parts? And do you find you need to ruggedize the hardware for space environment?
Yeah, so there were some particular items that if you were to use our software and want to bring in something that has a third-party software, you definitely may have the legal aspects of a lawyer having to go ask for permission to modify another COTS item to implement within this system. But overall, the software is ours as far as the architecture. And if you want to bring in a third-party piece of gear as some other software, that would be up to you to navigate that process. So what was the second question? I'm sorry.
It was do you follow a rigorous test regime for qualification of COTS parts, and do you need to ruggedize the hardware for space?
Yeah, so we did a subsystem by subsystem testing qualification program on this. And for example, the solar panels you see there, we put them through their paces quite a bit. Actually went to the extreme. We tried to break them, and actually the table that we were testing on limited out before we could break them. So we did do a fair amount of testing. We did do a thermal vacuum, actually a vacuum chamber test as well. We were preparing to launch this item at one point. It did not launch, but the good thing was it was kind of a test article that was discussed a lot within NASA, and as commercial launch vehicles were coming along and their development as well, it was very common for this particular satellite to be discussed with the main launch vendors. And I went to several launch vendors within the United States, and we talked about launching the system, and I think it kind of helped with other conversations for commercialization of spacecraft of this class and different scale. So it had its purpose in that way. But yes, we did do a fair amount of testing. It did not fly. So some things are TRL5, TRL6. And the approach of documentation as well on this spacecraft was different than the traditional NASA model as well. So it was more of experimental research type of approach to drop the cost, because labor is really some of the biggest price tag within this. So it's about $500,000 worth of parts, and we manufactured things that needed to be custom and tested them, and then other items we were testing in the environment lab to see how well it would work. The reaction wheels and one of these items we were testing as well. So what was the third question?
That was it. Those are the questions.
Okay.
Yeah, thank you. Appreciate it. And then we have the one last slide with your publications. If you want to, the web links, if you want to touch it real quick.
Yeah, this is just additional web links to some things that have been published on this technology. And I encourage you to go read these if you're interested in the technology. There's also a podcast kind of that I did with the Technology Transfer Office with the Tech Briefs magazine, talking about some of the intent of what we were trying to do with development of this spacecraft and how it could be applied in commercial industry. So I really thank you for your time, and appreciate it's an honor to participate in this. So thank you.
Yeah, no, thank you. This was all great. We appreciate it. Thank you for participating.
Thank you.
Next up, we have Arwen, who will be talking about affordable vehicle avionics, or AVA.
Hello. The AVA, or the Affordable Vehicle Avionics project, has been around well before I came on board. They have at least 6 years of the core team holding the project together through various project managers, of whom I am the final one. So I can explain it a bit to you all, but I can't take credit for this. This is the team. So I will speak more about them at the end if we have time. Next slide, please. So the concept of AVA was brought about from things like COTSAT, the presenter before me saying that they had this wonderful payload that could have gotten to orbit, but they had trouble finding a ride. We wanted to enable more payloads like that to find a ride. So AVA was made to reduce the cost of avionics. This small box you see in the illustration is just the hardware portion of AVA. It also is part software and part method. The method involves the user. So it's not as simple as it looks. The hardware is the simplest part. We use COTS sensors that normally you couldn't use in avionics, but we're enabled to do so by using a Kalman filter that allows us to take out the noise produced by the lower cost sensors and use it to guide launch vehicles. We've scaled it down by quite a bit from the original design that we started working with. It was originally about 5 kilograms. It's now under 1 kilogram, as you can see, about the size of a bacon, lettuce, and tomato sandwich. The cost was reduced by an order of magnitude from the conventional avionics at the time we started the project. At that time, the cost was $500K for the components. We've got it down to $6K for the components total. And it was in the millions for the software to integrate with the launch vehicle. And we've brought that down in our time to $42K. So each user will be taking a different method with AVA, and their costs may vary slightly, but we have made it to our goals for a project to reduce that cost by an order of magnitude. So now the users who will be taking this over from us as we license it can use it to get rockets to low Earth orbit. It can guide single or multi-stage launch vehicles, and it can guide spin stabilized or non-spinning rockets. We've worked out all the bugs using a good flight opportunities program that allowed us 2 launches to make this platform so it could work with a variety of other launch vehicles. The benefits of AVA is that it can reduce the avionics costs, as I've been said, by an order of magnitude. But what this really translates to is that smaller rockets can now afford to launch more frequently, and CubeSats can afford to ride up and provide the cost to cover the launch as primary payloads. That means you can specify your own launch and your own orbit parameters, and you don't have to hitchhike on the larger payloads that's being the primary. So CODSAT, we hope you get to fly. Next slide, please. The 2 flight opportunities program launches that we were able to avail ourselves of were in September of 2018 and November of 2019. The first was a single-stage rocket from Up Aerospace, and the second was a 2-stage rocket, which you can see in the 2 images to the right. And you can see we got up above the Earth's atmosphere and were able to take control of the rocket momentarily from the built-in system so that we can demonstrate our system, and then handed the control back to the rockets. So next slide, please. We were able to demonstrate almost all of the capabilities on these 2 flights, bringing it to TRL-7, the one exception being the 3-axis attitude control, which we did demonstrate on the ground, but for various reasons on the 2 other flights that had nothing to do with our avionics system, we were not allowed to demonstrate it. So whoever licenses this will be taking on that responsibility. We, the team, wanted to make sure everyone understands that. The licensees will be taking this method, and they'll be telling the software how many thrusters or other attitude control systems they have, what their geometric configuration is, and where's the center of mass, et cetera, et cetera. Whoever licenses this will be tailoring it to their vehicle, and will have to input those parameters into our software. Then they will go through a cycle where they tune the software using a simulation to show whether or not they've got it quite right to be able to control their launch vehicle. And we go through a few cycles of that. And then there's some ground testing that they will be expected to do. And then once they get it onto their rocket, they should be able to control their rocket using this method, this hardware, and this software. So we look forward to working with the folks that are already volunteering to license this. And we look forward to anybody else who has questions or would like to fly this. We'd like to see more payloads like CODSAT get to space. Thank you very much.
Thank you, Arlen. That was great. Thank you for explaining all that. One question we have is, what interfaces are used to integrate AVA into a vehicle?
Well, first of all, it has to interface with the propulsion system. So on one of our flights, the propulsion system interface was disconnected. So that's why we were unable, we were sending signals to it, but we were unable to control it. That interface is the primary important one. You can either interface it directly to onboard power, or you can have it carry its own battery pack. And it is not commanded from the ground. It has preset time intervals built in, and it uses feedback from the launch vehicle itself. So once it's on board, it does not communicate with the ground. You can retrieve it afterwards and retrieve any data logs that you wish. I hope that covers your question.
I think it does. I appreciate it. Thank you. And for the sake of time, we have 2 more presenters. So Arlen, thank you so much. That was really cool and interesting. Appreciate it.
Thanks, guys.
So next up, we have Peter talking about space optical communications using laser arrays for CubeSats. Peter, are you there?
Yes, I am.
Great. Take it away.
I'm going to talk on space optical communications using laser arrays for CubeSats in low Earth orbit and low lunar orbit. Next slide, please. This is a new method for space optical communication using laser arrays for CubeSats in LEO or LLO. The idea is to combine a lens system and vertical cavity surface emitting lasers, pixels, and photodetector arrays, both of which are mature technologies in a new way. Possible applications are fine pointing of laser beams, augments body pointing by CubeSats, optical multiple access, simultaneously communicate with ground stations at different locations, and wavelength division multiplexing, which will increase the data rate of the transmissions. The NASA Artemis program will include LunaNet, a lunar communications and navigation network. And if it had a constellation of CubeSats in LO, which is about 100 kilometers from the surface, that could form a part of LunaNet. In my computer simulations, this method has been applied for laser beam propagation for satellites in LEO and LLO, including NASA's optical communication and sensor demonstration. Next slide, please. A comparison to other methods. For fine pointing of laser beams, there's a method that uses a quad cell photodetector to refine the body pointing of the CubeSat under the T-Bird program of NASA. Another method uses a fast steering mirror for fine pointing, and that's the laser cube system, another method. Both these methods change the direction of the laser beam by moving physical parts or the CubeSat. The present method uses a laser array with different lasers for fine pointing. There's no physical moving, rather electronic switching on the nanosecond timescale, which is much faster. Another method is the optical multiple access. There's a method that uses separate telescopes and lasers for each direction. It's the Inter-Satellite Omnidirectional Optical Communicator, the ISOC program that NASA's funding. The present method is more compact, uses a laser VCSEL array, and one simple small telescope. Another application is wavelength division multiplexing. There's a method that uses a different lens system and uses only VCSEL arrays for open loop transmissions. A separate device is needed to provide closed loop transmissions, and this is by the company Optiplus. The present method uses a lens system that has been used in computer simulations for laser propagation at LEO and LLO distances. It can use VCSEL arrays for open loop transmissions or VCSEL photodetector arrays for closed loop transmissions. Next slide, please. Some additional features in the market assessments and a reference. This method does not use an optical amplifier. The optical power is obtained from the VCSELs in a cluster, which I'll explain later. No, it doesn't require an optical modem. Beam modulation is obtained from the well-known small signal current modulation. And this system is very small, it's simple, static, compact, and has small size, weight, and power. Now the market assessments, there have been two. One was a market assessment, and that recommendation was for broad pursuit, and said there's potential commercialization partners from the CubeSat sector, and in the report there's a lot of companies listed. The second assessment was recently, and it was for a commercial evaluation. And there are two patents and one that's pending. on this method. And there's a link there that provides more information. Next slide, please. Here's just a brief introduction to how things work. An incoming laser beam is transmitted from a ground terminal and it enters the lens system, which directs it to an element of the laser array. The angle determines which element of the array it is directed to. Each element consists of the VCSEL component photodetector pair. The photodetector detects the incoming beam, and the VCSEL component returns a strong modulated beam to the lens system, which sends it straight back to the ground terminal. As the incoming beam changes direction, this change is detected by the photodetectors, and a laser adjacent to the detecting photodetector is turned on to keep the outgoing beam on target, so you don't lose the signal. The laser beams overlap, and well, as I said, the signal is maintained. The VCSEL component may consist of a single VCSEL or a cluster of VCSELs, and I'll talk about that later. Next slide, please. To develop this in the laboratory, possible developers are Professor Kensho Kei, who's fabricated these VCSEL photodetector arrays, and Professor Govind Agrawal, who could do the preliminary testing of these arrays with lenses. And of course, they would use their laboratories. I've worked with both of these professors for several years now. Next slide, please. So here's a how the array would look. There's a candidate VCSEL photodetector array in the drawing, and it shows the photodetectors, which are quite large in area compared to the VCSEL clusters where the lasers are. In the past, Kensho Kei has fabricated these for other applications, and on the left is example of an array. The big white circles are the photodetectors, the pin detectors, and there's little black dots which are the laser arrays, or the lasers. And on the right is an example of a VCSEL pin couple. Again, the large circle is the pin detector, and the little dot in the center is the VCSEL. Next slide, please. My last slide, this is an example of a fabricated VCSEL cluster. It's a 19-element cluster at 980 nanometers. The bandwidth is 18 gigahertz, and the optical power output is 150 milliwatts, and the wall plug efficiency is 30%. And you can see on the left, the fabricated cluster, and on the right it shows some of the computed or experimentally determined results of that cluster, showing the bit error rate is very well behaved, and the eye diagrams are open. And these results were sent to me by Jim Lott, who I'm in contact with. And this is a recent paper about this development. And that's my last slide. Be happy to answer questions.
Thank you. That was great. We do have one question, but I think you may have answered it. Are you using 1.5 micrometer wavelength?
No, this is at this one's at 980 nanometers. Others are at 850. I have done work with Govind Agrawal in the past, in which we used VCSELs at 1550. Right now, the major development in VCSELs is at 850 or 980 nanometers.
Great. And then we have one more. is the 150 milliwatt power level for each element of the Viscal array, or is that the overall power output of the array?
In this example, that's the power of a cluster. And then you would have, this is one cluster of the array, and then you have an array of these. For example, you could have a cluster of 8 arrays, or 8 clusters. You could have an array of 8 clusters that would work for fine pointing from low Earth orbit or from low lunar orbit. And I'm going to put in a paper for Photonics West, and for low Earth orbit, 130 milliwatts would be adequate, and for low lunar orbit, it's would be 5 milliwatts would be adequate. So now these beams are they are more focused than the beams that were used in the NASA program for the Earth that I mentioned earlier, where the watts was 2 watts, and this would provide pointing at 130 milliwatts. The intensity at the target is the same, so it's the same irradiance at the target, but it's more focused than without using this fine pointing that is possible with this method of using an array. Each element of the array is a VCSEL or VCSEL cluster.
Thank you so much for explaining all that, and this is very informative, and hopefully people come away with it wanting to license it. Thank you so much.
Thank you.
And our next and last presenter is Shakib, and he will talk about Nanosatellite Launch Adapter System, or NLAS.
All right. So with all the great technologies out there, some of which we've seen, there needs to be a way to take all these technologies and put them on a launch vehicle, and then deploy them from the launch vehicle. So I'm going to be talking about one solution to that. It's the Nanosatellite Launch Adapter System, or NLAS, which is actually 3 independent, separate capabilities that are configurable, modular, and work interoperably with each other. It is a technology readiness level TRL9 system, and I'll focus a bit on the sequencer. But I'll start with the adapter, which is the structure that where nanosatellite deployers can be mounted to. It also takes the structural load for a primary spacecraft. Hopefully you can see that there. Raising the separation plane for a primary payload, and the final rocket stage in the launch vehicle. Now, these adapters were built so that they're backwards compatible with the popular Cal Poly P-Pod deployer. So various types of deployers could be mounted within that space. And then the adapters, expandability is a key feature. So these adapters could be stacked on top of each other, creating more space. So we also have the NASA dispenser, which is a 6U CubeSat deployer system. It has 2 actuators, so a single 6U could be deployed, as well as 2 independently deployed 3U configurations. And so we can see in the adapters that on one side, 2 of these 6U dispensers are loaded, and there are also 2 more on the other side. So 4 NASA dispensers with 8 actuations. And so, again, these could be used independently. You find a space within the launch vehicle and mount it and carry on with your mission with or without the adapter. And for deploying, you would need to route the proper signal for actuating the deployment mechanisms. So let's talk about that a little bit. You know, I'm going to focus on the third component, the sequencer, which is off in this little corner here, which is our patented technology. So what's required to deploy a spacecraft? Predominantly, you need to be able to source a certain amount of electrical current within a short time period to drive the actuators. And you have to do that for each actuator in the correct order and on the correct schedule. And so with trying to increase access to space and carry out launches, we're increasing the number of payloads per launch. The number of interfaces to manage for each deployment increases, the cabling complexity increases, the power needs increase, and then managing the sequences gets more complex from a launch integration perspective when you consider ride shares with multiple stakeholders, various customers, various different payload providers from different organizations. And so as a launch integrator, a goal is to minimize the complexity for the launch provider and minimize the number of resources that are needed for the launch vehicle itself. So let's look at some of the issues for providing a sequencer. So a sequencer predominantly must manage the timing, the scheduling, the order of the deployments, which doesn't maybe seem like much of a challenge on its face, but the timing needs to be accurate through various thermal environments. And it needs to accept a signal from the launch vehicle as an initiation command. Okay, so it also needs to be able to route power to the actuators. So this sequencer can accept power from the launch vehicle and route it to drive the actuators. But what about taking it a step further to reduce the resources needed from the launch vehicle? So what if the sequencer itself sourced the power? Okay, so if it has enough self-contained battery power, well, how does the sequencer effectively drive the large amount of electrical current to drive the actuators? And that's a different problem than just having batteries. And then the electronics themselves and the computing resources inside the sequencer, those take power as well. So where does that power come from? Well, got to use some of that power budget. We have to make sure that that does not act parasitically and devastate the power budget needed to drive those actuators, particularly for longer missions where it might take hours and hours before the first deployment occurs. So that actually drives the need for the electronics to be ultra low power consuming. We're talking microamps range. We have to solve that. We also, for this kind of system, it's not a technology demonstration, and this has got to be, this has to work in flight. So reliability is a key factor here, as we have to think about the design of the electronics for radiation robustness, and how do you deal with that from a hardware perspective and a software perspective? What about hardware redundancy and software redundancy, and file system management, redundant file system management? And even with all that, it's still possible to have a corruption of files. So how do you handle a scenario with a corrupt file? And what about things like handling noise on the initiation command line from the launch vehicle and potentially spurious spikes? We have to consider hardware approaches and software approaches. But what about a stuck actuator, and how do you handle that kind of scenario? What are some approaches to that? As well as various launch vehicles may have different signals that they could provide to initiate that sequence. So what about that? So these are all considerations and issues that we addressed and solved and built into the sequencer. Furthermore, when we were going for our first launch, it wasn't the scenario where the launch integrator actually were able to provide us with a sequence that was going to be utilized. In fact, there are many cases where a launch integrator may want to change that or may need to change that along the way. And so that's a key capability. So, a GUI seems obvious. But how do we design that product so that the user can be assured that the configuration that they set works? So the team, designed the user interface to ensure that a non-technical user can configure the order and the timing. can load the sequence, read the sequence back from the redundant files from the redundant hardware, visually inspect the files, but also have that GUI itself runs a sanity check and does its own file comparison and flags any discrepancies through that process. The user can also, run a full physical check on the sequencer, fully loaded, using some specialized electrical ground support equipment that was developed for this. But there's also that scenario where the user needs to be able to modify it once it's all integrated on the stack and payloads are loaded, and nightmare scenario, you don't want payloads popping out when they shouldn't be. So we also built in that capability where they could alter the sequence and run a full physical check, but with the final output power stage disabled so that nothing gets deployed. They could verify everything on the hardware, measure it, make sure that it works with our ground support equipment, and then arm it ready to go for launch. So talked about expandability as well. So, that's a key aspect of this sequencer too. In the picture here, we can see that, there's one sequencer configured for one adapter ring and 8 actuators. So this sequencer was designed for driving 8 outputs, but we also included a 9th auxiliary output that could be used to drive an actuator, but was specifically designed as an input to a secondary sequencer. And so now, with a single initiation command signal from the launch vehicle, you can drive initiating multiple sequencers in parallel or series or whatever timing protocol that you choose to do. And because the sequencers are self-contained, they bring their own power, it allows for a theoretical infinite expansion of the number of payloads that can be managed from a single launch with zero redesign. And the limits are really only restricted by the mass, volume, structural loads type of constraints and capabilities of the launch vehicle in question. So with all these considerations, we solved these problems, we built the hardware, ran thousands of test scenarios, and we went through full environmental qualifications, and the system launched and deployed without fault. If the first launch was in 2013 on the ORS-3 mission on board a Minotaur 1 launch vehicle. And for that day, it was a record breaking 29 deployed from a single launch. And I think, with the market out there and the number of users just increasing for the number of small spacecraft users out there, I think the demand for access to space is only increasing. And so this could be a key technology for making that process a lot easier to handle. That concludes it. Thanks.
Thank you. That was great. We have a question. So how much does NLAS change the integration time?
I don't have insight into that as far as what people might typically do. It's so dependent on the launch vehicle, the process that they might be using. It depends on the number of payloads. There's just so many factors. When it comes to, a sequencer, for example, if you're able to pull a sequencer off of the shelf, you could go ahead and program it and, test it, right away, right? So that's a capability that, is available. But I think there's just too many factors to be able to, give a reasonable answer for on that.
We have a couple more questions. So does the NLAS adapter replace the ESPA ring? If so, how does NLAS adapter compare to an ESPA ring? And what are the advantages of using NLAS adapter over a ESPA ring?
Yeah, so there are various adapters out there. I think there may be, I don't know too deeply the structural loads capabilities and the comparison between them. So sorry, I can't speak to that, but we could look into it. And, like I said, also with NLAS, there are 3 independent technologies. So, the dispenser, you could you could just fly a dispenser if you wanted to and adapt it onto another adapter system if you wanted to. You could use a sequencer. So we actually had flown the NLAS with various dispensers and other adapter systems as well. So that capability to mix and match exists. So I think it predominantly depends on whether you have a primary spacecraft, what the use case is for that, what's going to meet the need, and then go from there.
Great, thank you. So we have two more. Can NLAS launch tab and rail cubes, and does it include a mechanism for reducing, eliminating tumbling rates post-deployment? Post-deployment.
I don't think I'm familiar with those technologies. I don't think I can answer that.
Okay, yeah, no worries. Thank you. I appreciate all of what you said. That was really an awesome presentation. Thank you so much.
All right, thank you very much.
So everyone, I just wanted to share my screen real quick and show you how to learn more about those technologies. To apply for the license or to learn more about them, you can go to technology.nasa.gov, and it's going to be in one of these transfer features. And so if you click on the T2 webinar, you can see all of the different technologies. And if you click on one of these, it'll take you to that page. You can apply for the license or contact us when you would like to do that, if you have any questions. So that's it for today. Just wanted to say thank you again to everybody. If we didn't get to your questions during the Q&A session, we'll follow up with you via email within the next week. If you have additional questions, please feel free to submit them on the page that I linked, that I showed just right now. And you can go and click on the various different technologies and ask questions that way. Once again, we really appreciate you taking time out of your day to be with us today. Take care and have a nice rest of your week.